Okay. All right, so we'll start off here. All right, scholars, this is it, right? So we have today, and I think our last time meeting live like this is going to be Wednesday, right? I hope everyone is doing well. You know, as far as our assignments go, keep in mind that here. Oh, shoot, you a little too? Man. Ouch. So yeah, if you're just joining us, welcome. Let me see. So we're in the home stretch. We're going to meet today and Wednesday. We're going to use these days as review. So our focus for today is chapter 3. The final exam should become available to this upcoming. Let's see. It's upcoming Sunday and it's due. The hard deadline for all assignments is Friday, May 10th, so a week from this Friday, May 10th at 11:59 p.m., right? Okay, so in preparation for the final, my recommendation to maximize your scores, you should still be able to access everything we've done for the semester. So my recommendation, obviously, prioritize the exams because that's where you get the most bang for your bucks. Get those to you can still earn you can still earn to 95% on those assignments, which is huge. You know, I'm okay even if you sit down like collaborated or with a tutor or with myself. You know, it's okay. Um, and then the thing I would prioritize last is the homework. The homework is a lot of work for minimal points. And so what you're going to see us working on today, you all should be able to access it. It's just a review session for chapter 3. It's just random questions from chapter 3. Yeah. As usual, if you have questions, feel free to unmute yourself to get my attention that we can talk about it. But let's hop over here and kind of look at these assignments. So we're doing this chapter 3 final exam review. This is for practice, not graded, 145 questions. Let me see. Give me a random. Nope. Between 1 and almost. Give me a random. All right, we'll start with question 107. Rachel. Come on. Let's minimize. All right. Let me see. All right. So I'll sit you there so you can charge a bit. Let me see. It says a normal window is a rectangle with a semicircle on top. Now, this question comes from section 3.5, question 56. It says a normal window is a rectangle with a semicircle on top. Suppose the perimeter of a particular normal window is to be 22 feet. What should be its dimensions? What should its dimensions be in order to allow the maximum amount of light to enter the window? So we're limited by the perimeter being 22 feet, and we want to maximize the area of this guy. Okay. Oh, wait a minute. Is this from our text? Because let me say, like, if we think about the simple shapes here, we have what, a rectangle and a semicircle. Yeah. Okay. Let's just take some notes. So let me start by getting a copy of this guy. Let's see if I can make it a little bit bigger. All right, it's decent. Tacos for business. Yeah, that's right. All right. Okay. Let me grab this. We're gonna have to go with it. So we want to maximize the area, right? Where is this thing? So again, our goal, we like to maximize the area. So what we're going to do is find the area of the simple shapes and add them together. The area of a rectangle is what? Length times the width. So if x is the radius, then 2x should be that width. So the area of the rectangle should be what? 2x plus y. All right, so that's 2x plus y. And then the area of a circle is what? Pi r squared. So then it's half of that. So we're going to say plus half of pi, and r in this case is x squared. All right, one more of those, and then I got to disable the sounds because this is right there. Let's see. Can we get y in terms of x? Oh, and then the perimeter, right? They also gave us information about the perimeter. Okay, so if we're thinking about the perimeter, we know that this is what, 2x, this is also y, and then this is going to be half of the circumference, right? So let's write something for that. So then the perimeter, let me see, it looks like it's going to be 2y plus 2x. Circumference is what? Pi times diameter. So 2 pi r. So then half 2 pi r, right? So then half of 2 is just 1, so we can just get rid of all this. Okay. Oh, and then we're also given that the perimeter is limited to 22 feet. So this equals 22, okay? So it looks like we have 2 equations and 2 unknowns we should be able to solve. I mean, let's kind of keep going. So let's oh, and instead of r, that's supposed to be what? X right here? There's an X there. Okay. So from here, we can get y in terms of x, right? From that second equation, if we solve for y, we're going to if we solve for y, we're going to have what? 2y equals 22 minus 2x minus pi x, okay? Divide both sides by 2, y equals 11 minus x minus pi over 2x, okay? So that's y in terms of x. Then we can take that and plug it into the first equation, and then we want to maximize the guy. Let's keep trying. Let's keep going. So then we want to maximize the area. 2x. Now y is going to be this 11 minus x minus pi over 2x. Okay. And then plus 1/2 pi x squared. Okay. Let's see if we can kind of like combine like terms a bit and simplify this down. Now we have an x squared term, so I'm going to move that to the front. So it looks like we have like pi over 2x squared. So then we have 2 minus 1 plus pi over 2. So 1 minus pi over 2. Okay. So we'll say plus 1 minus pi over 2, whatever that number is, x, right? because it's a 2 minus 1 minus pi over 2. So 2 minus 1 is 1. I'm going to leave that as 1 minus pi over 2, right? So those are accounted for. Then we say plus x, right? So this is really just a quadratic. And again, our goal is we're trying to maximize this guy. So this is the area in terms of x. So now, at this point, remember, this is just some number, right? So we have x squared. We have an x squared term and an x. Notice the highest power is a 2. Should there be a negative somewhere? Let me see if we can find a negative, because that would help us. No. Let me think about it. Okay. Where's the y? 2y, not that one. The second one. Nope. Plus, yeah. It would be nice if that x squared term were negative. Okay, let me see something. Because it seems like this is a parabola that's opening upward. If it were opening down, then the max would occur at the vertex. I'm trying to think of what else could be our limiting factors. So I guess we would find the max, because x is limited. It can't be more. Obviously, it's probably not even going to be close to 22 feet, but it also can't be more than 22 feet, right? So we want to maximize this guy as x is between 0 to 22, somewhere in that range, right? So we want to maximize this guy somewhere between 0 and 22. Okay. Let me think. No, we don't need, the thing is, we don't need, like, I mean, we can, like, if we take the first derivative, that'll give us, like, the vertex. But the thing that's throwing me off is because it's opening upward. If it were opening downward, then I'd be like, let's go with it. We could find the vertex and we could find the endpoints. I feel like I'm missing something somewhere. I feel like there's a negative somewhere that I'm missing. Let me just check it one more time. Semicircle supposed perimeter. What should be the dimensions to maximize the area? Okay. So then the area of the rectangle is the length times the width. So that's, I found my mistake. All right. So the area of the rectangle is length times the width. I think I did length plus the width. So let's go back and make that adjustment, right? So here it is right here. So the area of the rectangle, this guy should have been the multiplication symbol. So I'll adjust it here. That should have been 2xy, right? So let's see how that affects it. And then the area of a circle, pi r squared. So then half of that, okay, that looks good. Okay, so let me make that adjustment. I'm gonna just get rid of all this other stuff and go from there. I think the perimeter, let me check the perimeter one more time. 2y plus 2x. I think the perimeter is fine. Okay, so I'm gonna make that adjustment for the area, and then I'm gonna get rid of all of this. Delete it. Okay. Okay. So now with that adjustment, let's try this again. Let me undo it. Went back a little bit too far. So man, writing on this tablet is like so nice. Like I make a mistake, I could just, undo for the most part. Okay, so now we have our y, right? We made that adjustment in the beginning. You see in purple, I think we had 2x plus y. That should have been 2x times y. So now what we're going to do is substitute this y into that first equation, right? So again, our goal, we're trying to maximize the area. It's going to be 2x times 11. I think this is going to give us a negative that we were looking for. Wow, that's trippy. 11 minus x minus pi over 2x, okay? And then plus 1/2 pi x squared. Okay, now let's distribute and simplify. So now we're going to get what? 22x minus 2x squared. Okay, if we distribute the 2's are gone. Minus pi x squared. Yeah, see, now we're getting the negative that we were looking for. Plus pi over 2 x squared. Okay. So all those x squared terms, if we, all right. So then -1 plus a half is a -1/2, or -pi/2. Let me see. So then it looks like we have -2 minus pi/2. That term times x squared. So that's negative, right? That's what we wanted. Okay. And then plus 22x. Again, our goal is to maximize the area, right? So now we got that negative leading coefficient that we were anticipating. Now that means that we have a U-shaped graph that's opening downward, and the max should occur at the vertex of the parabola, right? This is just a parabola that's opening downward. J. Okay, I think he just like logged in and off. Okay. So now we have a U-shaped curve that's opening downward, and the max should occur at the vertex. Now we could just use the vertex formula, or I guess it's in the spirit of it being, because the vertex formula is -b/2a, that's going to be the x coordinate. We could do that, or we could just look at the first derivative. Now, how simple would that be? Let's try the first derivative since this is calculus, right? If we look at the first derivative, it's going to occur when the first derivative is 0, right? That's going to be our critical value, right? So let's look at a prime, I guess I'll call it just the first derivative. If that 2 comes down, that coefficient is going to become -4 minus pi x plus 22. And you need parentheses like that. Okay. So then what we want to do is set this guy equal to 0 and solve. Let's see. So then ultimately it looks like we get x equals, down bottom looks like we get this -4 minus pi under a -22. So we can factor out all those negatives. 4 plus pi under 22. Okay, so that's our critical value. So then what we would do is show that on the left side of this critical value, the first derivative is positive, meaning the original function is increasing. On the right side of this critical value, we should get a negative in the first derivatives. It shows the original function is decreasing. And then, or we can look at the second derivative. If the second derivative is what, negative, that means it's going to be concave down. And I think the second derivative here is simple. I'm going to do that because it looks simple. So then a double prime in this case is just going to be this -4 minus pi, right? Because this guy goes to 0. And then we really just take the coefficient of this guy, which is a negative number, right? So we have our critical value of whatever this number is of 22/4 plus pi. The second derivative is negative, which means that the original function is concave down, which verifies that this is indeed a local maximum, right? So whatever this x value is, this should maximize our area. We'll use that for our x. And then we need to go back and find y. Okay. So we can just use our calculator. That was interesting. Okay. Let's do a new. That's fine. This one right here. Okay, that's looking good. Reload and refresh. Okay. So for x, we got 22/4 pi. 22 over, 4 plus pi. I don't know why I think it's just because of the end of the semester, and I'm like, my brain is like off. It's out for the summer. Okay, let's see. Let me see. Can I put this in? Let's go like this. Full screen. And then this guy, we want this one to be like over here. The height. Okay. The radius, so that's our x. Let me see. I don't know what happened to whatever we had, but that's okay. We'll do it again. Okay, so we got 22 over 4 plus pi. 22 divided by 4 plus pi. Okay. Okay, now let's see. Two decimal places here. I mean, that's fine for now, I guess. We got 3.08. What, feet? Mm-hmm. And then we need to go back and solve for y. Right here. First scroll up, come on. Right there, we plug in this x value right there. Okay. So I think what I'm gonna do is just make a quick equation. 11 minus x minus pi over 2. I think this should be okay, times x. I think this is okay to have it written. Okay, and then what I'm going to do is I'm going to say I want to evaluate that function at that answer that we just got. Okay, so our y, so x is 3.08, and it looks like y is the same value. Let me check and make sure I got it typed in properly. 11 minus x minus pi over 2 times x. I think it's okay. So it looks like we got the same thing for x and y, which is a little bit trippy. But that could be the case. So let's see if that works. 3.08 feet. Okay. Yeah, that's what we got. So let's go with it. Woo-hoo. That was an adventure. I don't know about you guys, but that felt like an adventure for me. Because I kept wanting to like do things from college algebra, but I was like, no, this isn't a college algebra course. Don't do that. Like, leave it with calculus. So I mean, that was an adventure. That was fun. Let's try another one. Generate. Let's go to question 125. All right, question 125. Right, sure. Okay. So this comes from section 3.6. I'm not sure what the abbreviation in ACQ stands for. The graph shows the marginal cost, C prime, and the marginal revenue, R prime, for producing X items. The horizontal line is the graph of the marginal revenue. The graph shows the marginal cost. Okay. The horizontal line is the graph of the marginal revenue. Write formulas for the revenue function and the marginal revenue function and interpret. Okay. Okay. Marginal cost and the marginal revenue. Write formulas for the revenue function and the marginal revenue function and interpret. Graph the marginal profit function. That's fine. And graph a possible profit function. Okay. So we have a couple of points. Let me see. It says the horizontal line is the marginal revenue. And it says that the horizontal line is basically R prime. Okay. So then if it's a constant, the integral of a constant is going to be what? That constant times x. So 5x. So are we saying that the revenue function would be 5x? Because if we took the derivative of 5x, we would just get 5, right? Plus some constant. Oh, but then they gave us 2 points, right? Let's write this out just a little bit. This is 125, and I think what I'll do is go like this. Just for a little bit of reference. Okay, we can't see that at all. Can I like zoom out some? No. I know that's a little weird on the left. I'm just using it as a reference. Okay. So again, this is question 125. This comes from section 3.6, whatever this ACQ.3 is, right? But it comes from section 3.6. So our claim is that our revenue function is 5x plus some constant. Any constant would do. Let me see. Do we have any other information? Right formulas for the revenue function and the marginal revenue function. It looks like R prime is 5. The selling price of each item. Okay, I might click review an example. Let me think about this for a moment. These are R prime, right? That's a quadratic. We could find that equation. We might need to finish this out actually, because this R prime function is just like 5. Is R prime is equal to 5. So we integrate, we get like, or it's not really the integral, but because I think integration really didn't come in. Well, wait a minute. But yeah, it should be 5x plus some constant. Maybe we can just go with 5x. Let me see something. We don't have it. Okay. The graph shows the marginal cost and the marginal revenue for producing X items. Marginal revenue, right? Formulas for the revenue function and marginal revenue function and interpret. The revenue function and the marginal revenue function. So the marginal looks like it's R equals 5. The selling price of each item for my revenue function, let me see, it's positive. Do we have any information about the original? I feel confident this is 5, but I'm thinking about the other one. I'm going to go ahead and submit that. Let me see the selling price of each item. So what does the marginal revenue tell us? Is that like the money generated from the production of one additional item? The marginal profit, because we're going to need that cost function. We might need to like the selling price of each item. It's $5. What is the y-axis? Number of items produced. So when we produce 3, what is this? What is the y-axis telling us? Nothing there. Let me see. I don't think it's going to give us anything there. Graph shows the marginal cost of producing. So that's the money. That's the value. All right. So the money generated if we produce and sell one item should be $5. 2 items, is it $5? The selling price of each item. So it looks like it's $5. I'm gonna go with $5. Let's see if that works. Right. So then our revenue function. Now there should be a plus C, but I don't think we've gotten to that point here. And I'll go back and we'll recap this. But we got 5x here. It should be plus C, but I'm going to try this. Okay, the marginal profit. Okay. Cost. So if C prime is a if C prime is a quadratic, then C should be a cubic, right? Because when you take the derivative, we got to finish with the quadratic. And we got R, right? So at this point, what we have, so let's put this all together. So our revenue fund, 5x was good, all right? Our cost function has to be some cubic function, something to the power of 3. Now let's see if we can kind of get some more details. Okay, so what we can do is find the equation of this given quadratic and then take the integral, right? So the general form of a quadratic, let's use the following. I'll do it like this. Y equals x minus h squared plus k. And there's an a there. Okay. So then the coordinates of our vertex, let me see, 7, I guess it's a 1. Okay, there it is. 7, 1. So then minus 7 and plus 1. So then minus 7 and plus 1. So right here. So if we plug in the vertex into this guy, minus 7 squared plus 1. Okay, so then to solve for a, we just plug in some point on this guy. Right now we're just building a function for this quadratic. We plugged in the vertex. What's another one that we have? It looks like when x is 1, y is 10. That looks simple enough. Or we can do 3, 5. So when x is 3, y is 5, right? So I'm gonna use the ordered pair 3, 5, because I'm just, let me see, 3 minus 7 squared plus 1 equals 5. Okay, so we have everything except for a. What is that? 16. 16a equals 4. Ooh. Looks like a equals 1 by 4. Okay, so then y equals 1 by 4 x minus 7 squared plus 1. Okay, so this looks like the equation for c prime. Okay. Okay, so we want to integrate this guy, right? Just to get our cost function. Okay, so then c of x, we use like the chain rule, so squared becomes cubed, and it looks like we're going to get 1 over 12 x minus 7 cubed. Let me think. When we take the derivative of this guy, we get our quarter, we get our square. We got to say times a negative 7. No, times 1. Let me think. If I take the derivative of this, that comes down, that's there, and we would say what? Times 1. So I think we would get that. Okay. So then we would say plus x. And then normally it would be plus some constant, but I don't think we have to do that here. So let's see if this works, right? If we take the derivative of this guy. The 3 comes down, we've gotten our quarter, we've gotten our 2. This persists. And then we would say what? Times 1. So that's in the clear. And the derivative of this guy is this. So I think this is good. Right? Okay. So if this is our cost function, I think we have everything that we need. Let me see here. Okay, so we want the profit function, the marginal profit function. Let's see, it should be revenue minus costs. Okay, let me kind of keep going with what I'm doing. So we have our cost function, we have our revenue function. I think earlier we said that our revenue function is 5x. Okay, so then that means our profit function would be the revenue minus the cost. Now that we got those original functions and provided that they're correct, so that should be 5x minus the cost function. So let me see, 1 over 12, x minus 7 cubed minus x. Okay, so that's revenue minus costs. Okay, let's keep going. It looks like a cubic function. Oh, and then we take the derivative, right? Because we want the marginal profit function. Let me simplify this guy down some. We got a negative 1 over 12, x minus 7 cubed. 5 minus x is a 4x, okay? So then the marginal profit function, we take the derivative, we get our negative 1 by 4. It is x minus 7 squared times 1. So I think that's okay, plus 4, okay? So now this is saying that the center is a downward facing parabola We go right 7 and up 4. Okay. So downward facing parabola that went right 7 and up 4. So based on that, come on. There we go. Right 7 and up 4, it should be C. That's the only one that did that. All right, this is an adventure 2. And we'll recap this. Sketch a possible graph of the profit function. Okay. So we got a cubic function that had a negative leading coefficient. A negative leading coefficient means it's going to go down to the right, and because it's an odd degree, the other side does the opposite. So the only one that goes down to the right and the other side does the opposite is A. Okay. I feel like there should totally be some questions here. And I low-key want to recap this one. Let me see. So for part A, write formulas for the revenue function, right? So for the revenue function, we see that the marginal revenue is given, right? So what that means is that this is the derivative of the function that we want. The derivative is a constant. The integral of a constant is just going to be that constant times x, right? So that's where we got the 5x from. All right, I'm just doing a recap as best I can. So r prime by itself was just 5, that constant function. So then for the selling price, for me, because I knew that the X was the number of items produced, and I knew that the Y was some kind of like monetary value. So then the selling price of each item was just $5. Like, no matter what, how many items you produce, they all sold for $5 each, right? They would increase their revenue by $5. So that's why I did $5 there. We took the integral of the constant 5 to get 5x. So that was the second part of A. And then the profit function. So for the profit function, we had our revenue function. We needed to build the cost function, right, from this marginal cost function, right? So if this is a parabola, when we go to take the integral, it needs to be a cubic, right? So first we found the equation of this parabola. We started with the general form of a quadratic, which was like a times x minus h squared plus k. We used the vertex of this guy, and we used a point on the graph to solve for a. Then we took the integral and checked to make sure that our integral was correct. And then once we took the integral, that was our cost function. Now that we have the revenue and the cost, then profit is revenue minus cost. Then we found our profit function, we took the derivative, and then from there, once we had our revenue function and our cost function, I feel like the rest of it kind of flowed. And periodically, we did need to take the derivative. That was an adventure. Let's keep going. Like, let's try to maximize this time. Like, it just, let's just try to keep going. So let's go to question 105. Okay, that's fine. I mean, this is like sticking in these middle questions, boy. All right, let me zoom in a little bit. Brain's like, you were really making me work today. I was like, yeah, I know it's a pain, but hey, we gotta we gotta do what we gotta do. Right? Okay. So let's see. It says a retail outlet for calculators sells 600 calculators a year. It costs $2 to store. Oh, this one is like, I remember this one. I don't like this one. $2 to store one calculator for a year. To reorder, there is a fixed cost of $6 plus $2.35 for each calculator. How many times per year should the store order calculators, and in what lot size, in order to minimize inventory costs? So if we can get a cost function, like a legit cost function, then we'd want to minimize it. To minimize what we would anticipate, we have our cost function. We have some range that we're considering on it. Like, it potentially could be like a quadratic with a positive leading coefficient. If that's the case, then, you would just minimize it, first derivative, find the vertex, that kind of stuff. Let's see. It sells 600 for the year. It costs $2 to store one calculator for a year. To reorder, there's a fixed cost of $6 plus should the store order calculators. Let me see. How many times? For each, a fixed cost of $6 plus $2.35 for each calculator. How many times per year should the store order calculators? and in what lot size in order to minimize inventory costs. 600 for the year. $2 to store one for the year. So it looks like, are we talking about how many they store versus how many they order? It costs $2 to store one for a year. There's a fixed cost of $6 plus this for each calculator. How many times should the store order calculators? And then what's to minimize inventory costs? Let me see if I have my view on this. I should have it on this one. I remember we did one like this before, and it was a little bit trippy. Let's look at view an example. Okay, so first make a list of the variables and the constants, right? To store one calculator for a year. So if they had one calculator, it would only cost them $2, right? Let me see. So how could we make a distinction between what's being stored and what's being reordered? Let's keep going. So we need some labels. Okay, so the carrying cost plus the order cost, that's fine. So first we want to focus on the yearly carrying cost. And what's X going to be? I guess okay, here it is. That's fine, let's keep going. Okay, let X be the lot size. Okay. So whatever our lot size is, how much does it cost us to store that, right? So if X is the lot size, for instance, in this one, the storing cost should be whatever 2 times X, $2 for each calculator, right? And then plus for however many they order, the lot size there is going to be 4 times X. Let me see. A fixed cost of $4 plus $2.35 for each X. So that's going to be $2.35 times X plus 4, right? For this one. Okay. Let's keep going. Okay. I think I see it. Hang on. So then if we take however many they're carrying, sales 900 for the year. Let's see. That's the last part that I need is how do we tie in the 900 between what they're storing and what they are reordering, right? Let's see. So the lot size is the largest number in X units to have representative. Use the average. This represents the average amount held in stock. See, yeah, we wouldn't have got that, right? To have a representative expression for the amount in stock at any one time in the period, use the average X over 2. This represents the average amount held in stock over the course of each time period. That's fine. So the amount held in stock would be, I guess, well, would that be 2 times that? Let's see, which is just X. Yeah, that's fine. So write an expression for the reorder costs. Okay. Start with the number of orders in that must be made in order to sell a total of 900 calculators, okay? Then write an expression for the cost of one order in terms of X. That's one order in terms of X, and then that's the average, okay? So then we have the average times one order. That's fine. Yeah, see, there was no way we were going to get that, like thinking through it. So something like this is like experiential. Like you're going through the homework, you see it, let me reference it, then you reference your homework, and then you pull it up. Now, one thing is, this is why it's like, this is like part of the reason why I structure things the way that I do. The final exam should become available this Sunday, right? And you have unlimited attempts for like 5 days, right? Because I do acknowledge that, like, these are kind of ridiculous, right? So I was like, okay, it's not proctored, essentially, and you can reference your homework. So, like, and you can ask around. You can ask, like, do a little bit of digging and research for something like this. I pulled up the viewing example, and once I found it, then I was like, oh, okay, and then you just kind of match it. All right, I think we have everything that we need. Let me see. So the reorder cost is that. So then our cost function is something like this. So then we can take this and basically match it to ours. For that first part, it was the average times the cost, $2. So that's going to be the same. So then for hours, right here. So then really all we really have to do is use this. So then once we have our cost function, I think we can take it. Like we can take this formula and then adjust it for hours and then go from there. Okay, so that's what I'm gonna do. I'm gonna get a copy of this guy and then adjust it for hours. And then I think we can take it from there. Because I knew that this one had like some trippy things going on that like is not obvious. So let's just get a copy of this. Let's copy and delete. Okay. And so what I'll do is I'll go here. Question 105. Sorry, my stuff is like throwing a tantrum. 105. There we go. This comes from section 3.5, question 49. Okay. So let's paste. Allow to paste. So now I think for that first part, ours was similar. So our cost function, because it was still $2 times the average amount in stock. So it was 2 times x over 2. So the first part was x, and then the part for reordering, instead of 900, we're going to put 600. Let's make that a little bit more clear. Okay. Oh, a fixed cost. Okay, $6 plus $2.35 for each one reordered. Okay. So then I think from here we're doing algebra to kind of move forward. So that's the most challenging part of that one. Come on. Let me see. How many times? So I think this will give us our lot size, but then what's the frequency? How often? Okay. So our goal is to minimize this guy, right? So let's go ahead and minimize this, and we'll get back to the other part. So if we want to minimize this guy, if our goal is to minimize the cost, let's expand this. This is probably the last one. Let's see, x plus 6 on 6 is 36. 3,600. Let's write it like this. 3,600 x to the minus 1. Okay. So those are going to cancel. Siri, what's 600 times 2.35?
600 times 2.35 is 1,410.
Okay, I think the x is canceled for that one. So if we look at C prime, let's see what happens. So that's a 1 minus 3,600 x to the minus 2. And that's gone. Okay. So I guess we look at the critical number. So let's set this guy equal to 0 and solve. Let me see. If we add, we'll get what? 3,600 over x squared equals 1. So then, will that help us? It looks like it's difference in squares, right? Yeah, that's fine. So then we get what? X squared equals 3,600. So then x equals plus or minus 60. And then we got to put it in context. So the lot size, and so I guess the negative doesn't make sense in the context of the problem. So the lot size, are we saying that the lot size should be 60 calculators? And then how often? Let's see. How many times? 60. Let's see. So I'll view an example. Okay. The reorder size must be at least 1 and no more than that. That's fine. Yeah, we got plus or minus 60. Okay, that's fine. Yeah, that's fine. And we should verify that this is indeed the minimum by looking at the second derivative. I'm just gonna kind of let that be. 60 is the minimum. Okay, so then we substitute this. So n is the frequency. So if we said 600 divided by 60, it looks like 10 times per year. Okay. Okay. So the store should order 60 calculators 10 times per year. 60 calculators. Man, that's a trippy one. Check. So, so again, I think the moral of the story with this one, something like this, you have to just lean on the fact that it's unlimited attempts and it's not proctored. Like, it's okay. Ask around. You can ask me. You can ask. You can reference your homework, because that's what I ended up doing. Right. I just clicked on the view an example. Now, obviously, on the exam, it doesn't tell you directly where it comes from, but if you can find it in the homework, you can use it as a reference. Right. We still get unlimited attempts, and the system is set to take your highest score. Okay. So these were interesting. I don't know why it stayed in like this business economic stuff the whole time, but I mean, this is business calculus, so I guess that's reasonable. Yeah. But I remember I've seen this one before. It's a little bit tricky. All right, gentlemen. So we're kind of out of time. We could possibly do one more, but I got to let me do one more. Let's go to question 34. Let's do one more right here. Okay, let's see. The computer video games can be delivered in one of two forms, digital or physical. Shows thousands of games delivered in physical formats since this. So notice a downward surge occurred when digital formats first became. First became more affordable and available. Completes. Is F prime of 2012 positive or negative? Let's see. So the slope of the tangent line at 2012 is negative, right? Because we don't have the original function. So F prime is the slope of the tangent line at a point, so it should be negative. If you had to guess, you have a 50% chance. But chance favors the prepared mind, right? What does the sign of F12 mean in Supersoft? Let me see. Thousands of games delivered. So the rate of delivery is decreasing. In 2012, the number of games delivered in physical format was decreasing. Use the graph to compute F prime of 2012 and 2008. Choose it. Okay, which would be low, which has, let me see. So 2012, we have the slope of the tangent line, and 2008 is more steep, right? More negative. So the absolute value of 2008 should be greater than the absolute value of 2012. Yeah, I think it's this one. Because in 2008, the slope of the tangent line is steeper than in 2012. So that means the number is larger. So if you consider the absolute value of that larger number, it should be larger, right? I know that's a little bit circular. Okay. I don't want to do more, but I got to get ready for my other class. I feel like there should be questions, but just hopefully, I'm here if you want
I
to ask. Yes, go ahead.
got a question. So I need help understanding on 3.1, number
Mm.
12.
Was that from the homework?
Yeah. Yes.
Can you click? You have it open right now?
Let me send it.
Yeah. Click on the Ask My Instructor. I'll pull it up. 3.1, number 12. Just let me know once you sent it. I think I got everybody that's going to be here, so I'll mark this guy as absent.
Sent it.
Okay, I got it. Oh, I need my list of graduating seniors. I see one student. Let's go ahead and submit that. I can do his. Are there any graduating seniors on the call right now? Tuesday, is that tomorrow? They need their grades tomorrow? Oh, yeah, that might be the case. Let me look at this. Data measures nutrition. Where does this come from? 3.1? Let me pull it up here.
Yeah.
Copy. Paste. Come on. Oh, there it is. Okay. Let me see. Regression function. Use a regression. Let me see. It says the data in the following. Here, can I just click a similar? I just want to do a similar. This is fine. We'll just kind of go with this. It says the data in the following table gives a measure of nutrition and the projected life expectancy for various countries. Use the data to answer the following questions. Use the regression to fit a cubic function to the data in the table where X is the measure of nutrition and Y is the life expectancy. Measures of nutrition. Okay, and life expectancy. Okay. Then fit a quartic function and decide which fits best. Choose the correct answer below. It sounds like something we do on a calculator. Both functions fit well. Is that it? Let me see. Because like in a there's formulas for that. Hang on. Where those coefficients coming from? Okay, so what I would do for something like this, yeah, it looks like. Okay, here, let me just show you. So here it is. We need a copy of this data where the X versus the Y, right? So this is like, now I'm working on a TI-83 Plus. I want to say you can do this on using like numbers or Excel as well, right?
Right.
So then let me see. So if I go to stats, if I go to edit, and I'm gonna put in the X and the Y's here. Let's see. So 995, 1009, 720. It's a little tedious because we need a copy. 1187. You got to be sure to type it properly. 756. 1162. 618. 1097. 1281. And 811. Okay, so those are our X's. Then Y was 75, 82, 67, 80, 75, 78, 60, 74, 78, and 73. Okay. So then for that first part, well, this is this example. This isn't, I'm just working to view an example for right now. Okay, so let's see if we can generate those coefficients. So then a line of best fit, let me see if I go to stats, calculate, I think it want a cubic regression. So that's number 6, right? And then 1.7786, yada, 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 negative 5.83. So that's where those coefficients come from. So you can see how they match. Graph the function on the graphing utility. So we can actually look at that. If we go to stat plot and turn the stats on, and then zoom stat. So number 9. Oh, and then we gotta do the graph. Y equals. Let me go back. How can we get to capture those? I mean, let me see. Let's see if I go alpha A. No, that's not it. How could I capture that? We just need like those, right? I think we did number cubic quadrant number 6. I'm trying to think if there's a way I can capture those. Like I want to store those to use. Let me see. I mean, we can just type them manually. So like for instance, if I do alpha A over here, I say 1 point, I just didn't want to type that out like that. 1.7786225 times 10 to the negative 7. I want to store that as alpha A. Okay. And then B is negative 5.80. And I feel like there is a faster way to do this. I'm just doing this way just for times 10 to the negative 4. Store that as alpha B. Okay, can't see the others. So I'm just going to recall them. Okay, so we got A and B. We need C. I guess we got it over here. We can use this. So then C is 0.630032, stored as alpha C. Okay. And then D is a negative 149.806712, stored as alpha D, stored as alpha D. Okay. So then once we have those stored like that, we can go to Y equals and just do alpha A. Let's try that again. Let me see. Alpha A x to the power of 3 plus B x squared plus C x plus D, right? We can just put it in like that. So now when we go back to our graph, okay, that's fine, right? So we get something like this, right, for that one. It looks a little different because of the window, but that's fine. Continue. And then so that was a cubic, right? If we want the quartic, we would go stat, calculate. Quartic is number 7, and it'll give us the coefficients for a quartic, so power 4, right? So it's just an extra coefficient in there. And then if we match it up to theirs, the first one is a negative 1 point, but that's how you generate those coefficients, right? That's the hardest part there, I think, in my opinion. And then stat plot and things of that nature. And so you can see the cubic function and the quadratic function are similar. All the points are located very close or on an line using the parts of the curve that falls. Both functions fit very well. All right. Then the domain, the x values, the min to the max. 618 is the minimum, 1281 is the max. So that's our domain. There may be a maximum near this point, but it's not absolutely clear. Okay. Let me see. What's the time? What's the domain, right? So you see the domain again. The domain was just the min to the max. Let me see. May have one near our max. So max y value. $83, $82. I see 83. 10. It might be one near 1027. 1100. That's fine. Let's see. It may have one. So I think it's either B or D. May have a relative max. Let me see. Okay. So we're saying a max. Let's go with, well, I'm gonna just show the completed. I was thinking D. B. Relative max. Yeah, sorry. We said the right thing, but we chose the wrong one, right? Or let me see. Yeah. Because it's basically with that part, it was flipping between may and definitely, and then you knew it was a max near 1100. But that was the meat. The meat and potatoes was really getting a copy of the data, putting it in a spreadsheet, and then now I was working on a TI-83 Plus. You can do something similar in like Mac numbers in the iOS or Excel. Like you just get a copy of the data, do a quick Google search on how to find a regression line for a cubic regression line or a quartic regression line. And it's a similar procedure. Then once you have those coefficients, then you have your, you can look at the graphs or whatever.
Okay.
Okay. Hopefully your question got answered. Are there any other questions? We're kind of out of time. So, we did the best we could there. Again, just do the best you can. Just do the best you can. Just take advantage of the unlimited attempts. Like that's about all I can say. Let's look at something real quick. I just want to glance at something. Oh, I think I do have I know I have at least one graduating senior. But maybe that's not today. Tomorrow. Hopefully that's not tomorrow. It might be. I gotta look at the date. I just want to look at something real quick. Oh, come on. Okay, there we go. And let's go to view. No, not view. Manage. Okay. Yeah, so that's this Sunday. Yeah, so the final becomes available this Sunday is due the following Friday. Are there any graduating seniors in here going once, going twice? Okay, I did get a notification from at least one. All right, gentlemen. So we gotta call it a day. So on Wednesday, that'll be our last time together. We'll work on chapter 4 and we'll do the best that we can. All right. All right. So with that, we're going to end the session here. And from one beautiful mind to another, take care, guys. Let me go ahead and make a copy of this available. All right. Let me share. Send it to box. Yeah, they get trippy. That's not the right for spring. Traditional calculus notes updated daily. This one. All right, guys, take care.